Hello everyone, this is Siavash Ibrahimian. Today my presentation is about the advancement in proton exchange membrane fuses performance. This is a subject of the renewable energy and energy storage. Today I'm gonna describing and analyzing the recent advancement to optimize of the proton exchange membrane fuse cells, electrode, and MEA membrane electrode assembly, with a focus on performance enhancement and platinum loading reduction, as well as improving the performance of the electrolyte, electrodes, catalyst layer, and membrane. Global warming is so dangerous and has a negative effect to our life. We need to have some acts now. Global warming and climate change are one of the most serious issues in the world. Unfortunately, the extensive research and development have been focused on reducing the pollution. The proton exchange membrane, also called as a polymer electrolyte membrane fuel cell, PEMFC, that has a solid polymer electrolyte to separate the fuel from the oxidant. The proton exchange membrane fuel cell is one of the most important sources of renewable energy, one of the cleanest, and one of the most efficient energy conversion devices due to the free of pollution and free of carbon dioxide emission. The proton exchange membrane fuel cell is widely used as an electrical energy producer device in vehicle transportation, which is the automotive industry, residential manufacturing companies, stationary power plants, and portable power generation systems. The proton exchange membrane fuel cells has a great improvement, has a great development in three main industries, such as the automotive industry, stationary power plants, and as well as the portable power generation systems. In 2015, the US Department of Energy declared the lifetime of hydrogen fuel cells vehicle energy system is improved from 5,000 hours to 6,700 hours, and for stationary power system is developed from 40,000 hours to 50,000 hours. The Japan's New Energy and Industrial Technology Development Organization could improve the PMFC power density to 6 kilowatt per liter last year, means in the year 2023, and they predict they can improve it to 9 kilowatt per liter by year 2040, like next 20 years. The proton exchange membrane effectively transports proton and an electron from one electrode to the other electrode, means from one anode to the other anode, and separate the fuel and oxidant. The proton exchange membrane fuel cells must be electron conductivity, proton conductivity, thermal and mechanical stability, and insulator between anode and cathode, and ability to prevent any kind of gas and liquid penetration. Must have a great isolation or insulator. The most popular material for low temperature of the PMFC is the perfluorinated sulfonic acid membrane, PFSA, which includes the Nafion membrane. And the most popular material for the high temperature is the polybenzimidazole film, or PBI film. Several membranes have been developed and successfully tested and applied in flexible proton exchange membrane fuel cells, such as the Nafion 117 membrane, that helps to improve the proton and electron conductivity at the low humidity and durability, as well as decrease the cost of the PMFC. Because the Nafion membrane is so flexible and has a great performance and very sensitive to humidity and temperature. The US Department of Energy approached in the year 2020 the power density to 2.5 kilowatt per liter, the specific power to 2 kilowatt per kilogram, and durability to 5,000 hours. The US Department of Energy predict the durability of the proton exchange membrane fuel cells will be developed to 8,000 hours in the year 2025. That means next year, they could improve the durability of the proton exchange membrane or polymer electrolyte membrane to 8,000 hours. This is a great development. This is a great improvement. So in this slide, we have two figures. The left-hand side figure is the future development plan that use the hydrogen as a fuel in different industries that increased from less 100 megatons to more than the 500 megatons from 2020 to the year 2050. And different colors shows, or different color is the different industries. The right-hand side figure is the zero emission buses in the state of California that shows the current and future development that buses replace the thermal engine with a hydrogen and fuel cell engine that shows from the year 2020 to the year 2050. This is a picture and a schematic of the proton exchange membrane fuel cells that has an internal special cooling supply, and also it has a membrane electrode assembly, which is the center and heart of the proton exchange membrane fuel cell, as well as it has a gas diffusion layer that covered by the gasket. It has two catalyst layers that act as an anodic and cathodic electrodes. Also, it has a bipolar place with an active area of 200 centimeters square. All these layers are sandwiched and assembled with the two metal plates like these two, and these two metal plates are assembled with a bolted. And hydrogen fuel cells has a two input and one output. One input that the hydrogen fuel goes into the system, and the other input is the air or oxygen that goes into the system. And also it has just one output. The output is a water steam. Also, the maximum current density of the proton exchange membrane fuel cells is around 450 milliamperes per centimeter square. The maximum current density of a PMFC is 450 milliamp per centimeter square. This is the current density of the PEMFC. The MEA stands for of the membrane electrode assembly. This is the heart of the fuel cells and working to optimize the performance of the fuel cell. The membrane electrode assembly has an anode, which is a negative electrode, where hydrogen is oxidized through the hydrogen oxidation reaction, HOR, and a cathode, which is a positive electrode, where oxygen is reduced through the oxygen reduction reaction. So we have a multiple method that helps to progress the MEA performance. One is using the platinum group metal alloys with inexpensive metal to create the novel catalyst. The second one is the ionomer, using the ionomer during the electrode fabrication to increase the platinum loading. Third one is the having better gas transport and increasing the electrical conductivity during the fuel cell operation. Another method is increase the contact surface area of a catalyst layer and triple phase boundary where proton, electron, and gas molecules meet. The catalyst layers are one of the most critical components in the fuel cell. This is a place where the electrochemical reaction occurs, and they are commonly fabricated by the ink composed of a platinum catalyst, ionomer, and solvent onto the membrane. So when the proton exchange membrane fuel cell is bent or twisted, the catalyst layer will be destroyed, and therefore the performance of the membrane electrode assembly get decreased and internal resistance of the catalyst layer get increases. Because the conventional catalyst layer have poor contact surface area with the membrane. So the suggested material to replace the conventional catalyst layer that have a poor contact surface area is the carbon fiber core, because the carbon fiber core has a great bendability, great flexibility, and improves the performance in a twisted compared to the conventional catalyst layer. And catalyst layer for flexible PMFC must be fabricated and designed rationally to improve the flexibility and catalyst structure, as well as increase the strength and interfacial contact surface area with the membrane. So in this slide, I provide the name of the manufacturing companies that design and produce the hydrogen fuel cells in different places of the world, including Canada, United States, China, Sweden, United Kingdom, Netherlands, Australia, and some other countries in the world. Conclusion, last but not least, proton exchange membrane fuel cell has a water-based, flexible, and solid electrode membrane that commonly use the Nafion membrane, platinum-based electrode, and operates at low temperature. For having the flexible proton exchange membrane fuel cells, it is necessary to replace the traditional catalyst layer, which is a conventional catalyst layer, gas diffusion layer, and bipolar plates with flexible material with high proton conductivity, high electron conductivity, and permeability features under the low humidity and low cost. The flexibility, durability, and performance of the proton exchange membrane fuel cells have been significantly progressed by improving the assembly techniques, increasing the fuse storage, decreasing the size and weight of the essential components of the proton exchange membrane fuel cells or polymer electrode membrane fuel cells. Like using the ultra-thin and flexible electrode that compose of a carbon nanotubes, which is the method to decrease the thickness and the weight of the proton exchange membrane fuel cell. Thank you so much. Thank you everyone for your listening and your patience. And I hope you have a wonderful and great day. See you later. And don't forget to like my presentation. Have a great day.